Alright, I'm going to talk about problem 19 from homework set 10a, where you find the coordinates of the point in the xyz on the plane z equals x plus 3y plus 1, and you're finding the point which is closest to the origin. The way I like to think about this problem is that you want to minimize the distance of this point. We'll say it's right here. You want to minimize the distance of that point from the origin. So for that we use our standard distance formula, x minus x initial squared plus y minus y initial squared plus z minus z initial squared, and that's all under a square root. And this is really nice because since we are right at the origin, the x initial, y initial, and z initial are all 0. So we can kind of just take them out when we solve this problem. What we want to do next is be able to represent z as a function of x and y, which we can do pretty easily using the plane equation. And then since the distance formula will use z squared, I'm just going to solve for that quickly right now. And then now we can do a function of x and y for the distance of the point to the origin. And I'm writing that out right here. And then now from here, just like we've done before for other optimization problems, you can take the partial derivative with respect to x and respect to y, so I'm going to do that here. And then once you have both of those partial derivatives for fx and fy, they're a bit complicated because of the square root, but we can simplify that pretty soon since we're going to set both of these partial derivatives obviously equal to 0, which means we can kind of just ignore the denominator and focus just on the top part of both of these partial derivatives. Then what we'll want to do next is combine these two equations so that we can eliminate a variable. I'm going to multiply the partial derivative of y by negative 4 over 6, which once we combine these equations will eliminate all the x values and leave us with just y, 6y minus 80 over 6y minus 2 equals 0. Using this, we can now solve for the y value, which comes down to negative 12 over 44. And then we can use this value, plug it back into our partial, and find the x value, which comes out to negative 4 over 44. At this point, I'm just going to simplify my x and y coordinate to make them a little easier to work with. Y becomes negative 3 over 44, and x becomes negative 1 over 11. And now with these 2 points, we can plug them into our original plane function to find the z value. So that's negative 1 over 11 plus 3 times negative 3 over 11 plus 1. And when you solve that all out, you get z equals 1 over 11. And with that, we have all 3 coordinates for our point in question. We know it's on the plane equation. It fulfills the plane equation that we were given. And in just a moment, I'll use the CalcPlot website to show you guys that point in plane so we can confirm that this point is indeed the closest to the origin. But before that, one thing I just want to, add in case we ever, encounter any problems like this in the future. The most important part is knowing where you're measuring to and understanding your plane equation. So if it was the coordinates of the point on the plane closest to, let's say, the point 1, 2, negative 5, you can still use that same distance equation, but just make x initial, y initial, and z initial the same as whatever point you're starting at or whatever point you're measuring to, which means Once you know how to solve one of these problems, you can kind of solve any of them. Alright, and now looking in the calc plot 3D applet, you can see there's our plane, there's that point, and no matter where you rotate it, you can definitely tell that point on the plane is the closest to the origin, and that's exactly what we were looking for. So, I hope this was helpful, and thank you for watching.